Now, in our previous two lectures, we discussed the basic properties of the nucleus. These include that the mass and binding energy of the nucleus, angular momentum, electric and magnetic moments, symmetry and parity. Now, the most important property of a nucleus is the determination of its mass or the binding energy in its ground state. As you know that the binding energy is written is this one. This is the binding energy. Now, what does it reflect? It reflects the effect of nuclear forces acting between the nucleons, which is attractive in nature, minus the electrostatic repulsion between the protons, and minus the insignificant binding energy of the atomic electrons. Therefore, it reflects the effects of the nuclear forces, effects of the nuclear forces is acting between nucleons, which is attractive in nature in the nucleus. The number of protons and A is the mass number, minus the effects of the repulsive forces between the protons and the insignificant atomic binding energy. Atomic binding energy. So here, how the nucleons are bound within the nucleus, that means in the case of the Coulomb repulsion, how they are packed together in a small volume, that is due to the very strong internucleon attractive forces. Now, the atomic masses or nuclear masses can be obtained. There are several methods. The most important one is the mass spectroscopic determination of the charge to mass ratio of a nucleus in the external electric and the magnetic field, or by determining the moment of inertia of a molecule in which one of the element is replaced by its another isotope, provided the actual mass of the one of the isotope should be properly known. So now we are not going to discuss the determination of the mass of the nucleus. Now here we concentrate on the binding energy. Now the binding energy is determined on the basis of a formal theory which is called the semi-empirical binding energy formula, which is based on the liquid draw model. Now the mass difference between the neighboring nuclides in the chart of the nuclear species reflects the binding energy of the last particle or particles. Now suppose first in the chart of nuclear species, that is hydrogen is 1, it is deuterium, then hydrogen 3, then you get helium 4, 11, 5. Now here only one proton, now this is the proton, now this is one proton, one neutron, one proton, two neutrons. Now the mass difference between these nucleus gives you the idea about the binding of the energy of the last particle or particles. But there is no formal theory which predicts the binding energy of a nucleus except for very light nuclei. The nucleus consisting of many nucleons, let us suppose say heavier nucleons, say oxygen 16 or say nitrogen 7, hydrogen 14. They are very much complicated in nature. As the number of nucleons will increase within the nucleus, the structure is very much complicated, and for these nucleons, there is no formal theory which can predict the correct binding energy of a nucleus, or say there is no such formal or say particular potential model nowadays still which can predict all the properties of the nuclei quite accurately. So there is nuclear force is still mysterious to us. Now, therefore, an empirical formula is attempts were made to find or to establish a formula which can predict the binding energy by considering several terms in which the nucleus is considered to be a drop of liquid of incompressible liquid and with a very high density. Now there are several factors in this formula. The one is the volume effect term, another is surface energy term, which is analogous to the surface tension of a liquid drop, and the electrostatic energy, because there are a number of protons, so there is a strong electrostatic energy is there. Now symmetry effect is there, pairing effect is there. Now therefore the mass difference between reverse neighboring nuclides in the chart of nuclear species reflects the binding energy last particle or particles. That is when from proton or say hydrogen it is formed a deuterium by adding another neutron, it forms bound state. Then from the difference one can get an idea that how the with which energy the neutron is bound with the proton. Now, but there is no formal theory which predicts the binding energy of a nucleus. Now, in the semi-empirical mass formula, in the semi-empirical mass or binding energy formula, the hierarchy feature of the nuclear forces are ignored. But the strong internuclear attraction is traced. Now, in this model, the nucleus may be considered as a drop of incompressible fluid. In this model, the nucleus may be considered as a drop of incompressible fluid with very high density. Now, this idea has been used together with other classical ideas like electrostatic repulsion, and surface tension. Etc. Now this formula contains several terms which are function of the atomic number and the mass number. Now this formula contains several terms that are functions of Z and A and weighting these factors with constants either derived from theory or experiment. But theory does not help, then we take the help of the experiment. From theory or experiment. But theory does not help. That means if we consider the several terms like say volume term, surface energy terms. So suppose a volume term, we consider a term say volume is a function of volume term, but it is multiplied by certain factor, suppose the CV. So this weighted average or these constant terms, these are determined from the theory, but theory is possible, or other from the experiment where the theory does not help. Now this semi-empirical mass formula, it contains several terms. Now the main factors which are contributed to the formula are the first is the volume term. The main factors which contribute are the first one is discussed, the volume term. Now the main contribution comes to this formula is from the volume effect term, in which it is assumed that the contribution to this binding energy is proportional to the volume of the nucleus. Because we know that the volume of a nucleus, as we have discussed earlier, that is proportional to the A, the mass number or the number of constituents particles in the nucleus. Therefore, because the internuclear forces between the two pairs of nucleons, either proton or neutron, so this will generate the main attractive term, and that is proportional to say the volume of the nucleus. Now therefore the main contribution comes from this volume term. Now this term expresses the fact that total binding energy is roughly proportional. The total binding energy is roughly proportional to the volume of the nucleus or to the mass number A that means we can write the relative contribution from the volume effect EV. Therefore, we write EV that is equal to minus CV E. EV is proportional to A, so this is proportionality constant. Minus stands for attractive in nature. Now, to justify this term, it is explained in this way that as the nuclear volume is proportional to A, so it is the number of nucleons in the nuclei. So this volume energy term will also be proportional to A. Now, since the nuclear forces are very short range, since the nuclear force are very short range, so a particular nucleon can see its neighboring nucleons only or interact with its neighboring nucleon only. Each particle will see each particle will see a certain number of neighbors around it. And the attractive forces from these neighbors will result in a binding energy which is proportional to the number of particles inside the nuclear volume, which is proportional to A. Now, if we consider the A number of nucleons inside a nucleus, now suppose a liquid drop, say A number of particles are here, okay, very closely packed. Now, consider this nucleon, this one. As the nuclear forces are very short range, only this will strongly interact with its neighboring nucleons. Similarly, this one will not strongly interact with this one or this one or this one. Similarly, this one will interact with this one, its neighboring. Okay. So in this way, actually, each nucleon will face the same amount of attractive forces roughly, except at the boundaries that we shall discuss, because the nucleons at the boundary they will be attracted in one side only. Now, therefore, if each nucleon, these attractive forces produces the binding, so this is roughly proportional to the number of nucleons A. This is the simplified explanation. So, the volume energy term is proportional to therefore A, the number of nucleons. Now, the next important term is the Coulomb electrostatic energy, because as you know, within the nucleus, Z number of protons are here, positively charged particles, they are closely packed, so there is a very strong electrostatic repulsion, although much less compared to the nuclear attraction, but still we have to calculate the electrostatic Coulomb energy of repulsion between the protons, which are very closely packed within a very small volume. So the next term is the electrostatic energy. Second one, electrostatic energy, which is repulsive in character. Now, suppose you consider this is the nucleus, where Z number of protons are closely packed, and the radius of this nucleus is R. So, the radius of the, if we consider R is the radius of the nucleus, if capital R is the radius of the nucleus or radius of the sphere, which you consider as a drop of liquid, then in that case we know that this R is equal to R0 to the power 1/3. Now we consider it is a proton sphere of radius R. Now the charge density, therefore, charge density of a proton sphere of say radius R, that is given by rho, that is equal to JD, Z number of protons are there, by the volume 4/3 pi R cubed. Now the potential due to such a sphere at the surface that means here at this point when r is small r is equal to capital R, therefore the potential due to a potential due to such a sphere at the surface that is V of R is 4/3 pi rho R square. That means VR is equal to JD by R charged by the distance capital R. Now JD is replaced by rho 4/3 pi R cube, so you get this formula. Okay. Now, so this is the potential at the surface of the nucleus of radius R. Now the electric field intensity, which is negative gradient of this potential, so electric field intensity or electric field for small r less than r, they within the nuclear volume, that is negative gradient of the potential, that is 4/3 pi rho r. Now if we integrate this equation, del V del R equal to this from say R to capital R, integrating the above equation from say small r to capital R, then one yields, and what we get? Small r to capital R minus del VR 4/3 pi rho small r to capital R that means here we get VR minus capital V, that will be equal to 2/3 pi rho R square minus small r square. Now therefore you can calculate VR by taking VR on that side. So if we calculate it, then small VR will come two-thirds pi rho 3 r square minus small r. Take this in this side, substitute its value at the surface and simplify, you get this one. Now if you substitute the value of rho here, putting rho in the above equation, what we get? VR JD by 2 R cube, JD by twice R cube into 3R square minus small r square. Potential at an inside point of that charged proton sphere. Now we have to calculate, this is the potential, now we calculate the potential energy because we are interested in the energy, not in the potential. Therefore the potential energy term due to this proton sphere, that is EC, electrostatic, say, Coulomb repulsion energy term, that is which is half from 0 to R. We have to integrate over the whole radius, rho dr into the volume element term for sphere 4 pi r square dr. So if we integrate this, substitute the value of dr here and integrate it from 0 to r. If we calculate all these steps, then finally you get this EC will be equal to 3 by 5 Z square is square by capital R. So this is the electrostatic Coulomb repulsion energy. 3 by 5 Z is square by, Z square is square of the charge. Now the Coulomb interaction, we know that the interaction between the Coulomb interaction is proportional between the number of proton pairs in the nucleus, because the interaction will be between two particles. Now therefore the Coulomb interaction is proportional to the number of protons Coulomb interaction is proportional to the number of proton pairs in the nucleus. Unlike the nuclear forces are very short range, so this proton will not interact with this one, or it will not interact with this one in nuclear forces, but Coulomb forces, this proton will interact with this proton will interact with this proton will interact with this. It's a long range potential, infinitely long range Coulomb potential. So the Coulomb interaction is proportional to the number of pairs. This, or say this, or this and this, and this and this. So we have to, suppose Z number of protons are there. So taking 2 together, what will be the number of pairs? So number of proton pairs will be equal to, by combination, therefore the number of proton pairs is Z into Z minus 1 by 2. That is equal to Z square by 2 minus Z by 2. Therefore, the Coulomb repulsion energy term, electrostatic repulsion. Now, neglecting the self energy term, what we get? The Coulomb electrostatic repulsion energy. We write it is that Cc Z into Z minus 1 divided by R. It was there divided by R. R is proportional to a to the power 1/3. So it is a to the power minus 1/3. Don't understand? Because Z into Z minus 1 by R was there in the energy term. So that R is replaced by A, because we mentioned here that all the factors will be expressed in terms of either Z or A for a nucleus. Now, if we neglect this term, self-energy term, then it will be approximately equal to C Z square A to the power minus 1/3. Okay, this is the Coulomb electrostatic repulsion term. Now, the next term is the surface tension energy or surface energy. As in the case of a liquid, we know that a very strong surface tension force is there. That's why a liquid takes the form of a sphere. Now, as in the, I try to understand that a number of nucleons are here, protons and neutrons. Only the nuclear force, which is very attractive, strongly attractive in nature, they interact only with its neighboring atom. This will nucleons. This will interact with this or this or this or this or this, but it will not strongly interact with this one, because nuclear force is very short range. It is far a large distance from this. Now, similarly, this will also attracted by these nucleons only. So all the nucleons inside, they are attracted almost equally by the same force. But it is true in case of nuclear, say, matter, infinite nuclear matter. If we consider the nucleus as an infinite dimension, then all the nucleons will be attracted by the same force, but it has a finite dimension. What about the nucleons which are at the surface? They will be attracted only one side only. This side, there are no nucleons which can attract them. So they are very strongly attracted towards the center. That means a very strong surface energy exists there. Okay. That means the strong attraction of these nucleons in the surface, they make the surface smaller and smaller, make the nucleus very compact. Now, that's why, like the surface tension of a liquid, so the surface energy is very important. The next term is the surface energy. Now, in writing, the volume energy term it is assumed that all nucleons are surrounded by other nucleons surrounded by other nucleons as would be the case infinite nuclear matter. If the nucleus is of infinite dimension, as in case of infinite nuclear matter. But in reality, the number of nucleons in the nucleus are finite. That means nuclear dimension is finite. So, the nucleons on the surface of the nucleus will be attracted by nucleons on one side. Outside the surface there are no nucleons, so only nucleons which are inside the nucleus, they will attract them. So that it results in a very strong surface energy, like the surface tension of a liquid. Hence, there is a positive surface energy which is analogous to the surface tension of a liquid. Okay, the strong surface energy term will be there. Now the surface energy, as the surface is involved, it is proportional. So the surface energy is proportional to the surface area of the nucleus. So the surface energy of a is proportional to the area of the nucleus. That is, we can write EA is surface energy term, that is CA. And what is the surface area of the sphere? 4 pi r square. 4 pi is a constant quantity that is taken inside it. R square, R is proportional to the a to the power 1/3, so it is a to the power 2/3. Okay, R square, R is proportional to 1/3, so R square is proportional to a to the power 2/3. So EA is CA into a to the power 2/3. So this is the surface energy term. Now these are the most important terms in the nuclear semiempirical binding energy formula. But besides this term, there is another term which is another two terms which are symmetry effect and pairing effect. Fourth one is symmetry effect. Now it is observed that the nuclei with Z is equal to N with Z is equal to N, that is proton and neutron number are same, are most stable, and it is a consequence of the exclusion principle. It is a consequence of the exclusion principle. Now, in the binding energy of the nuclear chart, you see there is a stability line for which Z is equal to N. For Z is equal to N, that means for those nucleus for which proton and neutron numbers are same, they are very much stable. Oxygen 16 is a very stable nucleus, Z is equal to 8, N equal to 8. Now, calcium 40, 20, 20, very stable. Now, we see that as the number of neutrons increases, that is in case of say heavier nuclei, say uranium and transuranium elements, Z is N is much larger than Z, so they deviates from the stability lines. So instability is there. Now, therefore, the nuclei with same number of protons and neutrons are the most stable one, and it is a consequence of the Pauli's exclusion principle. Now, suppose here the nuclear levels are filled by the protons and neutrons. The shaded are protons, suppose, and these are neutrons. So this is the nth state, psi n, of a particular nucleus. These are protons and this is a neutron. Now, if we want to add a proton here in this nucleus we want to add a proton, then the proton cannot stay here. We have to add the proton here. The proton will go to this level because these are two identical particles. All neutrons are identical particles and protons are identical particles. And two fermions, they are fermions, spin-half particles. So, for two fermions, they cannot have the same set of quantum numbers. Here, one proton, suppose A and A, everything is same, but one is spin up, another is spin down. Is up, one is minus up. That's why these two are here. Similarly, if we want to add another proton, this should go to this higher level, not here. But if we want to add a neutron, no problem, it comes here. So, these two nuclei, if you consider one same nuclear number A, but this one, but neutron is a this will be most of it has the lowest binding energy compared to this one. Okay. Now, therefore, of the two isobars, same number of A, so here of the two isobars, formed by either adding a proton or a neutron. The latter one, which is formed by adding a neutron, has the lowest binding energy. The latter will have the lowest binding energy. Lowest energy compared to the former one. So clearly there will be a term in the mass formula. So we have to take this effect into account. So clearly there will be a term in the binding energy formula which increases with the increasing value of with increasing value of Z minus N. So the symmetry energy symmetry it is CS A minus 2Z whole square. Now there is another term in the binding energy formula, that is pairing energy. Now I will see that when the nuclear levels are filled, the neutrons and protons are filled in pair. One is spin up, another is spin down. In this way, the two pairs are filling all the energy levels. Now, therefore, it is observed that the nucleates with even number of protons and neutrons are more stable. With the pairing energy, even number of protons and even number of neutrons are there. That means they form the pairs. So the nucleus with even number of protons and neutrons both are even, neutron number is even, proton number is even, are more stable. But there are exceptions also. For some light nuclei, there are exceptions. And nuclei with odd numbers of both protons and neutrons are least stable. While nuclei with either the proton or neutron number is revealed are intermediate in stability in between these two. While nuclei with either proton or neutron number reveal, either proton number is even, neutron number is even, are intermediate, but the another is odd. Instability. So this pairing effect also a very strong contribution in the semiempirical binding and formula. So this value of E delta, which is the pairing energy term, it depends on in the following way. So this is the mass number, proton number, neutron number, and here is E delta. First is even nuclei. A is even, Z is even, N is even, which is a minus. In this case, it is minus delta by twice A. One is A is odd. Either this is even, or this is odd, or this is odd, this is even. Suppose it is even, then it is odd. It is taken as 0. Similarly, here also. Now this is odd, and this is even. Here it is also taken as 0, and here say even, and both are say odd, proton number and neutron number, where it is plus delta y twice. So by considering this term, we can write the binding energy formula. Now, therefore, the binding energy formula, if we consider all these terms and write the binding energy formula, then we get so with all these terms, the binding energy formula is written as binding energy minus CV into A volume energy. Binding energy itself a negative quantity. Now plus the electrostatic energy term Z square to the power minus 1/3 plus the surface energy term which is proportional to the R square, that is A to the power 2/3 plus symmetry A inverse A minus 2Z whole square plus the E delta. Now the mass of this equation can be written in this form, that is, we know that binding energy is equal to the mass of the Z number of protons plus A minus Z number of neutron minus the atomic mass multiplied by c square. So mass of a particular atom, that can be written in this fashion, that Z number of mass of the proton or hydrogen atom plus A minus Z mass of the neutron minus the binding energy divided by c square. So this into c square, the binding energy into c square. It is written in this form. So now, therefore, if we substitute the value of this binding energy here, then we get an expression for this. Okay. So next I'll just start from this and find that its implication.